Hello everyone, my name is David Bell, and together along with my collaborator Serena Chin, we'd like to say thank you for stopping by our poster today. And without further ado, I will discuss our work using Gaussian process regression to predict mutant protein binding affinity. In this work, we are interested in the concept of molecular recognition and therapeutic design. We are focusing on the MHC2 antigen system, and so here we have an antigen binding to the MHC2 clef, which would then bind T cells and stimulate an immune response. In particular, we can mutate the antigen for increased or decreased immune response as mediated through its binding affinity. One of the ways we can do that is we can select a mutation, and then we can take the native mutation and mutate it to isoleucine and look at the differential binding affinity of that mutation. So in this example, we are mutating from a serine to isoleucine, but that's sort of a chance mutation. How do we select out of the 20 amino acids which residues to mutate to? Okay. Well, here what we do is we say, okay, let's start from a small mutant affinity subset and then predict the remaining 20 amino acids from that subset. So we start with an experimental or theoretical mutant affinity subset, and then we want to predict, and then we predict the remaining amino acids. So then the choice becomes, okay, so what is our choice of algorithm? What is our choice of interpolation to do this prediction? So there are many different considerations that go into the choice of interpolation scheme, and one of the most critical is your choice of features, your choice of feature set. And there are many different amino acid feature sets, but here what we found is that only two are needed, and those two are size, residue size, which we give as residue volume, as well as residue hydrophobicity. And whenever we plot all 20 amino acids on these axes, we see that each of the residues is distinguishable, and also these features have low correlation with each other, and so they make for really nice features for our regression model. Now that we have a choice of reaction coordinates, what do we choose, or what do we select as our algorithm for regression over our features? And here we selected Gaussian process regression to interpolate and predict binding affinities. Gaussian process regression is particularly well suited for many biological problems, as reviewed in this He et al. 2020 paper. One of the reasons for this is that it intrinsically predicts uncertainty. It's also an explainable AI method. It's not black box like many neural network methods, and so we understand what the parameters mean. And lastly, it's easily visualized for less than 3 features, which is what we are doing here. We have 2 features, and it can be easily visualized over our reaction coordinates. So in practice, this is how the Gaussian process regression method works. We have the MHC2 antigen system. We want to predict the binding affinities for this particular site. What we first do is we determine the binding affinities for a small residue subset. So here I'm showing the stars are the determined binding affinities, and then we predict the remaining residues as shown in black dots. And whenever we compare the actual surface to the predicted surface, we see that they are roughly similar, and that the predicted values, what we predict using Gaussian process regression, roughly agrees with the actual determined binding affinities. Here are the results for using Gaussian process regression to predict binding affinities based on free energy perturbation computed binding affinities. And what we see is that around K, or subset size of K equals 6 to K equals 8, the R-squared coefficient of determination is already very high, so it's very accurate. And the error of the prediction is also roughly around 1 kilocal per mole, which is roughly the accuracy of the free energy perturbation method. And so this tells us that for the free energy perturbation predicted binding affinities, subset size of K equals 6 to K equals 8 is pretty accurate. And here I'm showing another free energy surface for the free energy perturbation data set, and we see that the actual free energy surface agrees well with the K equals 6 predicted subset surface. This is the Gaussian process regression results for experimentally determined binding affinities from the IEDB data set. And what we see is that the average R squared value is relatively reasonable, but it's very low from the maximum R squared value. So some predictions we're doing really well, but whenever we average them out, they're lower. And so one of the questions we asked is why is our average value so much lower than our max? And what we found is that for the IEDB dataset, it has a peculiarity of the MHC2 antigen system. And that peculiarity is register shifts, where the antigen shifts from one register to the second register and introduces a completely different set of binding residues, so a completely different binding configuration. And whenever we accounted for this different binding configuration by manually separating out the residues that shifted registers and those that didn't, we found that the prediction could be statistically improved. Next, we built a register-constrained dataset using the NETMHCII web server, and we predicted the binding affinities for this data set, and what we found is that the R squared coefficient determination was higher than it was for the IEDB data set. Further, whenever we look at the ROC curves for this data set, we see very high AUC values, and so this is very desirable. It means that we can distinguish improved binding affinity residues from decreased binding affinity residues, and so this is very important for therapeutic design. Here I'm just showcasing the free energy surfaces from the NETMHCII dataset results, and as you can see, they agree very well between the predicted and the actual free energy surfaces. We'd also like to note that we think this method is generalizable beyond the MHC2 antigen system, and we think it can be used to predict mutant binding affinities for various protein-protein interaction systems. And lastly, I'd just like to say that this work is posted on bioRxiv and hopefully to be published soon. It's under review, and we'd like to say thanks again for stopping by, and please stop by the poster presentation if you have any questions. So thank you for your time.